The process in a power plant involves converting energy from various sources into electrical power, which is then distributed for use. The process varies depending on the type of power plant, but the general steps are as follows. 1. Energy source collection. Power plants use different sources of energy, including fossil fuels, coal, oil, natural gas, burned to produce heat. Nuclear. Uses nuclear fission to generate heat. Renewables, hydro, solar, wind, geothermal, biomass, convert natural forces into electricity. 2. Heat generation for thermal power plants. In fossil fuel and nuclear plants, fuel is burned or nuclear reactions generate heat. This heat is used to boil water and produce steam. 3. Steam or mechanical power production. The high-pressure steam or other mechanical means such as flowing water in hydroelectric plants or wind and wind turbines drives a turbine. In solar and wind plants, turbines are directly driven by wind or solar heat. For electricity generation, the turbine is connected to a generator, which converts mechanical energy into electrical energy using electromagnetic induction. 5. Voltage regulation and transmission. The generated electricity passes through a transformer to increase voltage for long-distance transmission. High-voltage electricity is sent through power lines to substations. 6. Distribution and use. At substations, transformers reduce voltage for safe distribution to homes, businesses, and industries. Consumers receive electricity through local distribution networks. Detailed process of power generation in different types of power plants. Power plants work by converting different forms of energy into electricity. The main types of power plants include thermal power plants, hydroelectric power plants, nuclear power plants, wind power plants, and solar power plants. Below is a breakdown of the processes in each. 1. Thermal power plants, coal, oil, natural gas. Thermal power plants burn fossil fuels to generate heat, which is then converted into electrical energy. Step-by-step process. Fuel combustion. Coal, oil, or natural gas is burned in a boiler to generate heat. The heat converts water into steam at high pressure. Steam drives the turbine. A high-pressure steam flows through a steam turbine, causing it to spin. The turbine is connected to a generator, which produces electricity. Cooling and condensation. After passing through the turbine, the steam is cooled in a condenser using cooling water. The cooled steam turns back into water and is recycled into the boiler. Power transmission. The electricity produced is sent to a transformer, which increases the voltage for efficient long-distance transmission. It then travels through power lines to homes and industries. 2. Nuclear power plants. Nuclear power plants operate similarly to thermal plants but use nuclear fission instead of burning fossil fuels. Step-by-step process. Nuclear fission reaction. Uranium or plutonium fuel rods undergo fission, releasing a large amount of heat. This heat is used to boil water and produce steam. Steam drives the turbine. Like in thermal plants, the high-pressure steam drives a turbine connected to a generator. Cooling system. The used steam is cooled and condensed in a cooling tower before being reused. A cooling system ensures that the reactor remains at a safe operating temperature. Electricity transmission. The generator produces electricity, which is sent to transformers for distribution. 3. Hydroelectric power plants. Hydropower plants generate electricity using the kinetic energy of flowing water. Step-by-step process. Water flow control. Water from a dam or river is stored and released through penstocks large pipes. Turbine rotation. The fast-moving water hits turbine blades, making them spin. The turbine is connected to a generator, converting mechanical energy into electrical energy. Electricity transmission. The generated electricity is sent to transformers for distribution. Water recycling. The water is released back into the river with minimal environmental impact. For wind power plants. Wind power plants convert wind energy into electricity using wind turbines. Step-by-step process. Wind turns the blades. Wind flows over the turbine blades, causing them to rotate. Turbine rotation drives a generator. The blades are connected to a shaft, which spins a generator. Electricity production and transmission. The generator produces electricity, which is transmitted through power lines. The power is stepped up or down using transformers. 5. Solar power plants. Solar power plants use sunlight to generate electricity either through photovoltaic PV panels or solar thermal technology. Photovoltaic PV solar power process. Sunlight absorption. Solar panels absorb sunlight, exciting electrons in silicon cells. Electricity generation. This generates direct current DC electricity. Power transmission. The electricity is sent to the grid for distribution. Solar thermal power process. Sunlight concentration. Mirrors or lenses focus sunlight onto a receiver. Heat conversion. The receiver heats a fluid, producing steam. Turbine and generator. The steam drives a turbine connected to a generator to produce electricity. Final step, electricity distribution. Regardless of the power plant type, the generated electricity follows the same distribution steps. Step-up transformer. Increases voltage for transmission over long distances. Transmission lines. Carry high-voltage electricity across cities and regions. Step-down transformer. Reduces voltage before distribution to homes and businesses. Local distribution network. Delivers electricity to consumers. In-depth analysis of power plant operations. Each type of power plant operates differently based on its primary energy source. Below is a detailed breakdown of how each power plant functions, including advanced processes, efficiency factors, environmental impacts, and future developments. 1. Fossil fuel power plants, coal, oil, natural gas. These plants generate electricity by burning fossil fuels, primarily coal, oil, or natural gas, in a boiler to produce steam. Detailed steps. Fuel handling and preparation. Coal is crushed into fine powder for better combustion efficiency. Natural gas is directly piped into the plant. Oil is preheated to improve flow and combustion. Combustion process. Fuel is burned in a boiler furnace, releasing heat energy. This heat converts water into steam under high pressure. Turbine operation and electricity generation. The high-pressure steam is directed onto the blades of a steam turbine, making it spin. The turbine is connected to a generator, which converts mechanical energy into electrical energy through electromagnetic induction. Cooling and condensation. The steam, after passing through the turbine, enters a condenser, where it is cooled down using water from cooling towers. It turns back into water and is recirculated into the boiler. Flue gas treatment and emission control. Electrostatic precipitators or bag filters remove particulate matter from exhaust gases. Flue gas desulfurization (FGD) systems reduce sulfur dioxide emissions. Carbon capture technologies are being developed to lower CO emissions. Efficiency and challenges. Efficiency. 33 to 45%. Modern plants with combined cycle technology can reach 60%. Environmental impact. High CO emissions, air pollution, and water usage. Future trends. Carbon capture, cleaner coal technology, and transition to natural gas. 2. Nuclear power plants. Nuclear power plants use the fission process to generate heat instead of burning fossil fuels. Detailed steps. Nuclear fission reaction. Enriched uranium-235 or plutonium-239 undergoes fission in a reactor core, splitting atoms to release energy. This heat is absorbed by a coolant, water, or liquid sodium. Heat exchange and steam production. The coolant transfers heat to a steam generator, producing high-pressure steam. Turbine and generator process. Steam rotates a turbine, which drives a generator to produce electricity. Cooling and recycling. After passing through the turbine, the steam is cooled, condensed, and recirculated. Cooling is often done using a cooling tower or direct water exchange with rivers. Radioactive waste management. Spent nuclear fuel is stored in cooling pools or dry casks for long-term disposal. Some countries use nuclear reprocessing to recycle usable fuel. Efficiency and challenges. Efficiency. 33 to 37%. Advanced reactors can reach 45%. Environmental impact. Low CO emissions but generates radioactive waste. Future trends. Next-gen reactors, SMRs, thorium reactors, nuclear fusion research. 3. Hydroelectric power plants. These plants harness the energy of moving water to generate electricity. Detailed steps. Water storage and flow control. Water is stored in a reservoir behind a dam. Flow is controlled using penstocks large pipes. Turbine operation. Gravity-driven water flows through turbine blades, making them spin. The turbine is connected to a generator, which produces electricity. Water recycling and environmental considerations. The water is released back into the river with minimal pollution. Fish ladders, or bypass systems, help aquatic life migration. Efficiency and challenges. Efficiency. 80 to 90% highest efficiency among power plants. Environmental impact. Can alter ecosystems, displace communities. Future trends. pumped storage hydro run-of-river systems, floating hydro plants, FERT, wind power plants. Wind turbines convert kinetic energy from the wind into electricity. Detailed steps. Wind capture. Wind flows over the blades of a turbine, making them rotate. The yaw system adjusts blade direction for maximum wind exposure. Gearbox and generator process. A gearbox increases rotational speed. The turbine drives a generator, converting motion into electricity. Grid connection and energy storage. Power is sent to a transformer for voltage adjustments. Energy can be stored in battery systems or integrated with smart grids. Efficiency and challenges. Efficiency. 35 to 45%. Offshore wind farms can reach 50%. Environmental impact. No emissions but may affect bird populations. Future trends. Floating wind farms. AI-driven turbine efficiency. 5 solar power plants. Solar power uses sunlight to generate electricity through two main methods: photovoltaic PV and concentrated solar power, CSP. Photovoltaic PV solar process. Sunlight absorption. Solar panels made of silicon cells absorb sunlight. This excites electrons, generating direct current DC electricity. Conversion to AC. An inverter converts DC to alternating current AC for grid use. Concentrated solar power, CSP process. Sunlight concentration. Mirrors focus sunlight onto a central tower, or solar troughs. Heat is used to boil a fluid molten salt or water, to produce steam. Turbine and generator. The steam drives a turbine, generating electricity. Energy storage, CSP systems, store heat in molten salt tanks for electricity generation at night. Efficiency and challenges. Efficiency PV. 15 to 22%, CSP, 35 to 40%. Environmental impact, minimal, but panel production involves mining. Future trends, perovskite, solar cells, floating solar farms, solar batteries. Comparison of power plants. Type of plant efficiency, CO emissions, cost reliability, scalability. Fossil fuel coal, 33 to 45% high, low high. Natural gas, 50 to 60% moderate, medium high. Nuclear 33 to 37% none high, very high, medium. Hydroelectric 80 to 90% none medium, very high, limited. Wind 35 to 45% none low, variable high. Solar PV, 15 to 22% none medium, variable high. Solar CSP, 35 to 40% none high medium limited. Future of power generation. Smart grids, AI-driven electricity distribution for better efficiency. Energy storage, advanced battery tech, to store renewable energy. Fusion power, next-gen nuclear energy with zero radioactive waste. Carbon capture. Reducing emissions from fossil fuel plants, advanced power plant technologies and future innovations. As global energy demand increases, power generation technologies continue to evolve. Below, we explore advanced power plant technologies, efficiency improvements, environmental concerns, and the future of energy production. 1. Advanced fossil fuel power plants. Fossil fuel plants have been the backbone of electricity generation, but modern technologies are improving efficiency and reducing emissions. Supercritical and ultra-supercritical coal plants operate at higher temperature over 600 degrees Celsius, and pressure above 22.1 MPa, improving efficiency. Ultra-supercritical plants can achieve 45 to 50% efficiency, compared to 33 to 38% for conventional coal plants. Reduces coal consumption and CO emissions per unit of electricity. Integrated gasification, combined cycle IGCC, converts coal into syngas, a mixture of hydrogen and carbon monoxide, before burning it in a gas turbine. Achieves higher efficiency, approximately 50%, and allows for carbon capture and storage, CCS integration. Carbon capture, utilization, and storage. CCUS, captures CO before it is released into the atmosphere. The captured CO can be stored underground or used in enhanced oil recovery. Challenges, high cost, energy-intensive process. Future outlook, transitioning from coal to natural gas, and eventually to hydrogen-based power. 2. Next-generation nuclear reactors. Modern nuclear power plants are designed to be safer, more efficient, and produce less waste. Small modular reactors, SMRs. Compact, factory-built reactors with scalability and enhanced safety features, can be deployed in remote locations or integrated into existing grids. lower upfront capital costs compared to traditional reactors. Examples: molten salt reactors, MSRS, use liquid fuel, preventing meltdowns. High temperature gas reactors, HTGRS, produce hydrogen as a byproduct. No radioactive waste, unlimited fuel supply, and higher energy yield. Major projects: ITER International Thermonuclear Experimental Reactor aims to demonstrate commercial fusion feasibility by the 2030s. Private companies like Helion and Commonwealth Fusion Systems are accelerating fusion development. Future outlook: SMRS and nuclear fusion could revolutionize clean energy. 3. Hydroelectric innovations. Hydropower is one of the oldest and most reliable energy sources, but new technologies are improving its sustainability. A pumped storage hydropower (PSH) acts as a giant battery, storing excess electricity by pumping water uphill and releasing it to generate power when needed. Improves grid reliability and integration with renewables. B. Floating hydropower. Uses floating turbines in reservoirs or oceans, minimizing land impact. Can be combined with floating solar panels for hybrid energy production. C. Tidal and wave energy. Uses the motion of ocean tides and waves to drive turbines. Still in early stages, our will focus on environmental sustainability and energy storage. For wind power innovations. Wind energy is becoming one of the cheapest and fastest growing power sources of floating offshore wind farms. Unlike traditional turbines fixed to the seabed, floating turbines can be installed in deep waters where wind speeds are higher. Example: Highwind Scotland, the world's first floating wind farm. BAI-optimized wind farms. Machine learning algorithms optimize turbine performance based on real-time weather conditions. AI helps predict maintenance needs, reducing downtime and costs. C. Vertical axis wind turbines (VAWTs). Unlike traditional horizontal axis turbines, VAWTs can capture wind from any direction, more compact and suitable for urban environments. Future outlook: bigger turbines. Next-generation solar cells that are cheaper, more efficient, and flexible. Can be printed on thin films, enabling wearable and portable solar panels. Expected to surpass silicon-based panels in efficiency greater than 30%. B. Floating solar farms. Solar panels installed on water bodies, lakes, reservoirs, oceans. Reduces water evaporation and maximizes space usage. C. Solar-powered production for energy storage and industrial use. Future outlook: more efficient panels, solar-powered hydrogen, and AI-driven grid integration. 6. Energy storage and smart grids. As renewable energy adoption increases, energy storage and smart grids will play a key role. A. Advanced battery storage. Lithium-ion batteries dominate today, but solid-state batteries promise higher energy density and faster charging. Gravity-based storage, such as Energy Vault, lifts heavy blocks when power is abundant and drops them to generate electricity when needed. B. Hydrogen energy storage. Excess electricity is used to produce hydrogen, which can be stored and later converted back into power. Key to long-term renewable energy storage. C. AI and smart grids. AI-driven power grids balance energy supply and demand in real time. Predictive analytics help prevent blackouts and optimize power distribution. Future outlook: smart grids will integrate AI, storage, and renewables for a decentralized energy system. Final thoughts. The future of power generation. The global energy landscape is shifting towards sustainability, efficiency, and decentralization. Key trends shaping the future include: renewables overtaking fossil fuels in total energy generation. Fusion energy breakthroughs could lead to unlimited clean power. Smart grids plus AI advancements ensuring stable power supply. Hydrogen economy support. Cutting-edge innovations and global trends. As the world transitions toward cleaner, more efficient and sustainable power generation, emerging technologies are pushing the boundaries of what's possible. Below we'll explore breakthrough innovations, futuristic energy concepts, and global trends shaping the next generation of power plants. 1. The hydrogen economy. Powering the future. Hydrogen is increasingly seen as a clean energy carrier that can replace fossil fuels across multiple industries. A hydrogen power plants. Power plants can be retrofitted to burn hydrogen instead. Japan's hydrogen pilot project, the world's first hydrogen-based power station, opened in Fukushima, Japan, paving the way for large-scale adoption. B. Green hydrogen versus blue hydrogen. Green hydrogen, produced using electrolysis powered by renewable energy, 100% clean. Blue hydrogen, produced from natural gas, but with carbon capture to reduce emissions. Future outlook. Hydrogen could become the dominant fuel for energy storage, transportation, and industrial processes. 2. Fusion energy. The holy grail of power generation. Unlike nuclear fission, fusion does not produce radioactive waste and has an unlimited fuel supply from hydrogen isotopes. A key fusion technologies. Magnetic confinement fusion. Uses strong magnetic fields to confine plasma at high temperatures. Example, ITER, in France. Inertial confinement fusion. Uses lasers to compress and heat hydrogen fuel. Example, NIF in the USA. B. Breakthroughs in fusion power. In 2022, the National Ignition Facility, NIF in California achieved net energy gain in a fusion reaction, marking a major milestone. Private companies like Helion Energy and Commonwealth Fusion Systems aim for commercial fusion reactors by 2035. Future outlook. If successful, fusion could replace all fossil fuels and provide near unlimited clean power. 3. Space-based solar power, SBSP. Instead of relying on ground-based solar panels, space-based solar power collects solar energy in orbit and beams it to Earth.